See, we shall discuss about the chemical kinetics, that is JEE main exam chemistry. We'll discuss about the synopsis of the main points to be remembered. See, first one, see, mainly we'll discuss in chemical kinetics, that is rate of reaction. Rate of reaction. See, rate of reaction means the speed of the reaction or the velocity of the reaction, we can say that is rate of reaction. See, we are in physical chemistry, therefore we can represent the rate of reaction mathematically as a dx divided by dt. If I am considering the reaction, that is A plus B gives rise to C plus D. Here we can consider AB are the reactants and CD are the products. If we are considered, that is irreversible reaction. If it comes the rate of reaction of the reactant, that need to represent it as a minus dx by dt. If I am taken x as a concentration of reactant, then for the product we need to write that is d plus dx by dt. See, why we need to mention that is by negative sign? Because here, while happening of the reaction, the reactant going together to takes place the reaction, therefore there is automatically decreasing of concentration. So negative sign represent the decreasing of concentration of that is case of reactant. If it comes to the product side, there is an increasing of the concentration, therefore will represent that is by positive side. So these are all the simple description about the rate of reaction. Second point. See, how do we write the rate expressions for different chemical reactions? Rate expressions. For example, if I am considering the rate equation that is H2 plus I2 gives rise to 2HI. This you can write as the formation of hydrogen iodide. So if we need to write the rate expression for this equation, we have to write like this. See, these two are the reactants. Therefore, reactant concentration goes on decreasing while happening of the reaction. Therefore, minus d of concentration of H2 with respect to the time, that's is equals to minus d of I2, so with respect to the time, that's is equals to, now I need to write positive sign because this is the product, therefore that will becomes 1 by 2 into rate of change of HI with respect to the time. So this is the rate expression for the equation what I am considered here, that is the formation of hydrogen iodide. Next, third synopsis. See, I was gave only the description about the rate of reaction. See, rate of reaction does depends upon the many factors. While you learning the main concepts of the chemical kinetics, you was learn the point that is first one. The rate of reaction does depends upon the term concentration. So now there is a rising of question how the concentration does depends upon the rate of reaction. Here we can agree rate of reaction does directly depends on concentration. From writing the rate expression for the different equation, we'll become to know rate of reaction does directly depends on concentration. And second term we can say that is temperature. Now there is a rising of question how the temperature does depends upon the rate of reaction. According to the Arrhenius equation or Arrhenius concept, we can conclude rate of reaction does depends upon temperature. Then the third point you can say that is catalyst. So first of all, what is meant by catalyst? See, catalyst is the substance which is used to increase the rate of reaction. Means there is a rising question, is it the catalyst will not used to decrease the rate of reaction, which is the substance is used to decrease the rate of reaction, that is called as the inhibitors. Therefore, catalyst is used to increase only the rate of reaction. This is used to decrease the rate of reaction. Therefore, we can conclude here rate of reaction does depends upon concentration, temperature, catalyst. We can write one more point, that is nature of reactant also. Nature of reactants. So all the 4 points does depends upon the rate of reaction. Now we'll pass on to the next synopsis. Synopsis number 4, that is order of reaction. Order of reaction. See, what you can say the definition for order of reaction. If I am consider the example of that is rate reaction, A plus B gives rise to C plus D. Here I'll consider that is X number of A, then Y number of B. This is P number of C, then Q number of D. If I am apply the law of mass action for this equation, we can write that is dx divided by dt, means that is rate is directly proportional to the concentration of the reactants. Therefore, we can write that is concentration of A to the power of X into concentration of B to the power of Y. Now, if we remove the proportionality constant, we get that is constant, that is rate is equals to, if we remove the proportionality, we get constant, I will take that is K. So, K into concentration of A to the power of X into concentration of B to the power of Y. Now there is arising of question, what is this K? See, this K is called as the rate constant. Okay, therefore now to say the answer for order of reaction, order is equals to X plus Y, I can say that is a mathematical definition. Now there is arising of question now, so what we can say the simple definition for order of reaction. See, order of reaction is the sum of the powers of the concentration of the reactants of experimentally determined rate equation. So this is the simple definition for order of reaction. Next, fifth, number 5. So molecularity. So it is very simple definition we can give for molecularity. So if I am considering this the rate equation, in that rate equation, see how many number of molecules going to react to form the product, that is called as the molecularity of the reaction. Therefore we can conclude here molecularity is the theoretical value, but order is the experimental value. Therefore, we can decide here order does depends upon the experimental reaction. Molecularity does depends upon only that is number of molecules going to react to takes place the reaction to form the product. Next, number C. See, rate expressions, rate constants for different order of reactions. Means, see, in the order of reaction we can classify as a different kinds of order of reaction, as like zero order reaction, then first order reaction, second order reaction, etc. These are all the classifications of order of reaction. Now after mentioning that is different kinds of order of reaction, we need to mention the example for order of reaction. I will take that is dissociation of hydrogen peroxide, H2O2. If I am considering the dissociation of hydrogen peroxide, we can write that is there is a formation of H2O plus of O2, we can write. See here, this is the experimental rate equation. So, by the experimental rate equation, we can decide here rate is directly proportional to the concentration of H2O2, that is 0. Therefore, we can say this is the very good example for zero order reaction. Then I will come to the first order reaction. For the first order reaction, we can say that is dissociation of hydrogen iodide or decomposition of hydrogen iodide. I will take that is hydrogen iodide. Hydrogen iodide decomposes to form that is H2 plus Hi2. So to balance the equation, I need to write that is 2Hi. So here 2Hi leads to formation of that is Hi2 plus H2. So this is the very good example for first order reaction. Then I'll come to the second order reaction. For the second order reaction, we can take that is reverse equation, means formation of hydrogen iodide. H2 plus I2 gives rise to 2Hi. Here we can consider there is a concentration of H2, means rate is directly proportional to concentration of H2 into concentration of I2. If I am considering concentration of this is 1 and concentration of this is 1, order is equals to 1 plus 1 is equals to 2. So these are all the different kinds of order of reaction, and what I has given the example, these are all the different examples for different order of reaction. Next synopsis, integrated rate constant for zero and first order reactions. Already we had discussed about the different rate constant formula for zero order as well as the first order reaction while we learning the basic concept of chemical kinetics. Now, the integrated formula of zero order reaction, that is K is equals to concentration of R naught minus concentration of R divided by T. So this is the rate constant formula for zero order reaction. Now here we can consider R naught is the initial concentration, R is the final concentration, and time taken to complete the chemical reaction. Now we need to derive the one more formula of that is called as half-life period of the zero order reaction. While I am deriving the formula for half-life period of zero order reaction, here we need to consider that is, if I am taken R initial concentration half-life period. While you are considering half-life period, here this is the final concentration, this is initial concentration. See, there is no change in initial concentration, but there is a change in final concentration. At time t is equals to 0, if I am consider fact time t is equals to 0, R concentration of R is equals to concentration of R naught, we can write. So now we need to derive for half-life period, therefore K is equals to R naught minus, what will be the value of R at time t is equals to 0 if I am taken R is equals to R naught. If I am taken T is equals to T off, if I am taken T is equals to T off, then we can decide concentration of R is equals to half of concentration of R naught. Therefore now formula will become, so that is K is equals to R naught concentration minus 1 by 2 into concentration of R naught divided by T off it will becomes, because as taken T is equals to T off. Therefore total formula it will becomes 1 minus off is off, therefore 1 by 2 into concentration of R naught divided by T off. We need to derive the formula for T off, therefore T off is equals to R naught concentration of R naught divided by 2K. So this is the expression for half-life period of what? Zero order reaction. We will discuss integrated rate constant formula for first order reaction. Already we had discussed while we are learning the basic concept of chemical kinetics, that is rate constant formula for first order reaction, that is equals to 1 by T into ln concentration of R naught divided by concentration of R. Here K is the rate constant of first order reaction, R naught is the initial concentration, R is the final concentration. Otherwise we can write one more way also. If you are consider ln is equals to 2.303 into log, we can write this. Therefore if we substitute the value for here, that is ln, so 1 by T into 2.303 log of initial concentration divided by final concentration. Therefore, so this is the rate constant formula for what? First order reaction. Then we need to derive the formula for half-life period of the first order reaction. I'll consider when so T is equals to 0, concentration of R is equals to concentration of R, means we can consider that is initial concentration. Now if I am taken T is equals to T of initial concentration R, this is the final concentration. So if I am taken T is equals to 0, final concentration is equals to initial concentration. Now if I am taken T is equals to T of, then R gives rise to half of initial concentration, that will becomes. Now if I am substitute the values to the rate equation, that is K is equals to 2.303 divided by T of it will becomes, because I am deriving the formula for T of into log of, this is R naught divided by 1 by 2 into R naught it will comes. Now R0 get cancelled. So now 2.303 divided by T of it to log of 2 goes to the numerator. It will become log 2. Therefore, now 2.303 into log 2 value 0.3010 divided by T of. We need to derive the formula for T of. Therefore, T of is equals to 0.693 divided by K. So this is the half-life period formula for first order reaction. Next synopsis, that is Arrhenius equation. Arrhenius says that the rate equation, that is K is equals to A into e to the power of minus EA divided by RT. So this is the Arrhenius equation. Already as said previously, there is a relation between the rate constant to the temperature. This relation was given by the scientist. His name is Arrhenius. Therefore, we need to say that is Arrhenius equation. Here we can say this is K is the rate constant, A is the Arrhenius constant, A is activation energy, R is the gas constant, and T is the temperature. If I am consider the Arrhenius equation for different rate constant, then we can write that is K2 divided by K1. This is the total formula I am writing. So log of K2 by K1 is equals to EA divided by 2.303 R into T2 minus T1 divided by T1 into T2. So this is the formula is used to calculate different chemical rate equations of the rate constant, and also you can find out the what temperature. By knowing the temperature you can find out the rate constant. By knowing the rate constant you can find out the temperature as well as the what activation energy. This is called as the activation energy. Now last, that is see next synopsis, effect of catalyst on rate of reaction. See, while I am saying the factor that depends upon the rate of reaction, as introduced the word that is catalyst, but I didn't cite how the catalyst depends upon the rate of reaction. So if you use the rate of reaction, if we use the catalyst, how the rate of reaction get increases or get decreases. See, there is no arising of doubt decreasing, because I am using the word here catalyst. If we use the catalyst, there is need to increase only the rate of reaction. Therefore, so here effect of catalyst on rate of reaction. If you use the catalyst, there is an increasing of the rate of reaction. That you can explain by using the graphical representation. So here I will consider that is activation energy. Here I will consider that is reaction coordinates. So now if you draw the graph, see, if we didn't use the catalyst, the curve will come like this. But if we use the catalyst, the curve will come like this. So here we can decide here the activation energy without using the catalyst, it will become more. This is the activation energy without using catalyst. So this is the first curve. Next, the second curve, it is, if you use the catalyst, this is the curve what you will get from the graphical representation. This is the activation energy, this is the second curve. So here we can conclude neatly, if we didn't use the catalyst, it will activation energy is more. It will absorb the more energy to take place the reaction. But if you use the catalyst, it will require only the small amount of energy to take place the what? Chemical reaction. Therefore, we can conclude here there is an effect on the rate of reaction of that is catalyst. Therefore, we can decide here the catalyst does do the effects on chemical reaction. See, next we'll pass on to the problem. The first problem, ethylene is produced by C4Hi, gives rise to 2C2H4. The rate constant is 2.3 into 10 to the power of minus 4 second inverse. Approximately in what time will molar ratio of ethylene to cyclobutane in mixture attain the value equals to 1? Means we have to calculate your time. Here they gave that is rate constant. So that is second inverse means it should be rate constant of first order reaction. Therefore, I'll write the formula here. K is equals to 2.303 divided by T log of we can write that is initial concentration divided by final concentration. See, initial concentration if I am taken A, so that is A, final concentration we can write that is A minus X. Oh, so we can write in terms of 2.303 by T log of A divided by A minus X also we can write. Therefore, A divided by A minus X, initial concentration, final concentration. Now they gave the value of rate constant, we need to find out the value of time. So but we don't know the initial concentration as well as the final concentration. Now to get the value of that is A and A minus X, I'll consider the equation C4H8 gives rise to 2C2H4. This is the decomposition reaction. Now moles at time t is equals to 0, so the concentration of C4H8, I take this is A, initial concentration. If as I am taking here time is equals to 0, therefore the product formation is nil, therefore I will take this is 0. Now I will take at time t is equals to t. If I am consider the time t is equals to t, now at time t is equals to t, I have taken it is a happening of some time. So here initial concentration of the reactant I have taken A. In that initial concentration, some amount of the reactant to be converted as a product. I will take the converted product as a X. Therefore, after time t, what will be the remaining concentration? I can take that is A minus X. Now, if it comes to the product side, what will be the concentration after time t? We can take that is 2x because that is 2 molecule. Therefore, I need to take that is 2x. Now, if I am taken the ratio that is 2x divided by A minus X is equals to 1. Then if you have done the cross multiplication, 2x is equals to A minus X. Therefore, A is equals to 3x it will becomes. I need to find the value for x. Therefore, x is equals to A divided by 3 it will becomes. Now, I need to substitute the value for x, that is A divided by 3. Now I will substitute the value now, that is K value is 2.3 into 10 to the power of minus 4 is equals to 2.303 divided by time you have to calculate, just keep as like. Now log of, what is the value of A? We don't know. A divided by, so what is the value of A minus X is A divided by 3 it will becomes. Now, so we need to find the value of t. T is equals to 2.303 divided by 2.3 into 10 to the power of minus 4. I will simplify this. 3a minus a divided by 3. So now 3 goes to the numerator. Log of 3a divided by 2a it will becomes. So now a get cancelled. Now t is equals to 2.303 divided by 2.3 into 10 to the power of minus 4. If it will comes here, it will become plus 4 into log of, we can write it as a log 3 minus log 2. Now, t is equals to 2.303 into 10 to the power of 4 divided by 2.3 into, so log 3 value is 0.4771 minus log 2 value is 0.3010. Now, so t is equals to, if we simplify all the values, we'll get the answer, that is 1700 second. So therefore, we can say that is the time taken for that mixture to attain the value that is equals to 1. It will take, that is 1700 seconds. What is the half-life of a radioactive substance is 87.5% of any given amount of the substance disintegrates in 40 minutes. Means we have to find out here half-life period of the reaction, that is first order reaction. Therefore, half-life period formula, that is T of is equals to 0.693 divided by K. So, to find the value for T of, we need to know the value of K, rate constant. But if you see the problem, they didn't give the value for K. So, therefore, I need to find out the value of K first. K is equals to 2.303 by T log of A divided by A minus X. Initial concentration divided by final concentration. Now, see, they didn't give that is initial concentration also. Therefore, I will take that is let initial mass. They are saying that a radioactive substance. Therefore, let initial mass. I will take that is equals to A. In that initial mass, they are saying that. See, what is the half-life of a radioactive substance is 87.5% of any given amount of the substance. Therefore, if I am taken that is initial concentration will be A, then after time T, we can write that is after time T, X is equals to 0.875 A times 0.875 A times. They gave in what is that percentage as converted into the value 0.875 A it comes. Then substitute the value. Anyway, they gave that is T is equals to 40 minutes. K is equals to 2.303 divided by 40 into log of A divided by 1 minus, I take here this is A also, right? Therefore, A minus 0.875 A it comes. Now see, A divided by A minus 0.875 A. You can take A as a common factor, 1 minus 875 it becomes. Therefore, we can write that is A divided by A into, if we subtract the value, 0.125 will get. Therefore, A get cancelled. Then 1 divided by 0.125, that will becomes the 8. Therefore, K is equals to 2.303 divided by 40 into log 8 it comes. Now, so K is equals to 2.303 divided by 40 into log 8 value is 0.9030 it will becomes. Now, if we will simplify the value for K get the value. We'll get the answer for K 0.05 and will comes. Then what will be the SI unit for K? See here. So the concentration get cancelled, remaining only that is time. Time comes to the numerator. They give time in minute. Therefore, it becomes minute inverse. Or you can write that is per minute also. Now I need to find out the value of T of. T of is equals to 0.693 divided by K value. K is 0.051 minute inverse. If we simplify the value, we will get an answer 13.58 minute inverse comes to the numerator, means it will becomes minute. It will take 13.58 minutes of half-life period. Next we'll pass on to the third problem now. So T1/4 can be taken as the time taken for the concentration of the reactant to drop to 3/4 its initial value. If the rate constant for a first order reaction is K, the T1/4 can be written as. So now we need to find the value for T1/4. So I'll write the formula for first order reaction to find out rate constant, that is K is equals to 2.303 divided by T log of initial concentration divided by final concentration, A divided by A minus X. Now we need to find the value for T1/4. Therefore, is it they gave the value for K? No, they didn't give the value for K. Means you need to keep the answer in terms of what? T1/4. Therefore, T is equals to T1/4. Now, So this is initial concentration, this is final concentration. So initial concentration will not change, there is a changing of only final concentration. Here A minus X is there. What is the value of X now? X will becomes 1 by 4. Become I am taking time, T is equals to T 1 by 4. If I am taken T of X is equals to 1 by 2. If I am taken T 1 by 4 means X is equals to 1 by 4. I will give the values now. K is equals to 2.303 divided by T 1 by 4 log of A divided by A minus, so it will become 1 by 4, right? So A divided by 4 you can write, that is. Now, so now K is equals to 2.303 divided by T1 by 4 log of, so A divided by, if I am taken A common factor, so 1 minus 1 by 4 it will becomes, totally you can write that is 3 by 4. A get cancelled. Now that is equals to 2.303. We need to find the value for T1 by 4. I will take that is T1 by 4 to the numerator. T1 by 4 that is equals to 2.303 by K. So log, you can write it as a log 3 minus log 4 you can write. Is it? No. So 4 goes to the numerator. Therefore, so log 4 minus log 3 it will becomes. Now that is equals to 2.303 by K. See, log 4 value is 0.6020 minus log 3 value is 0.4771. If we will subtract the value, so 2.303 divided by K, so if we will subtract this value, we will get a value 0.1249. We will get a value, that is. So therefore, for T 1 by 4, now I have the value that is T1 by 4 is equals to 2.03 by K into 0.1249. If you multiply the value, that is T1 by 4 is equals to 0.29 divided by K. So this is the value for T1 by 4 for the problem. Next, we'll pass on to the next question. The reaction A gives rise to B follows first order kinetics. The time taken for 0.8 mole of A to produce 0.6 mole of B is 1 hour. Then, what is the time taken for conversion of 0.9 mole of A to produce 0.675 mole of B? So, they are saying here the first order kinetics. Therefore, I will consider the equation for first order kinetics, that is A gives rise to product. So this is the first order kinetic. So here they are saying that, so 0.8 mole of A to produce 0.6 mole of B. So now I will write the formula to find out the rate constant of first order kinetics. K is equals to 2.303 divided by T into log of A divided by A minus X, it will comes. Now this is initial concentration. They are mentioning initial concentration is 0.8. Then so converted will be 0.6. They are not saying A minus X. X is 0.6. Therefore now 2.303 divided by T. Is it they are mentioning the time T? So T, they are saying 1 hour, so it will becomes 1 hour. 2.303 divided by 1. So log of A they gave 0.8 divided by A minus X. A is 0.8. They are mentioning here 0.8. Then X is 0.6. What is the total value now? 0.8 minus 0.6. That will become 0.2. So now you can write it as a 8 by 2, that will becomes 4. Therefore, K is equals to 2.303 into log 4. Can write. So this is the value for K. For the next they are saying that what is the time taken for the conversion of 0.9 mole of A to produce 0.675 mole of B. Now I'll write the formula. K is equals to, this is for second condition, this is for first condition. I am deriving the answer for second condition. 2.303 divided by T log of C. Initial concentration they are saying here 0.9. I'll write that is 0.9 divided by so this is converted concentration, therefore 0.9 minus 0.675. So 0.9 minus 0.675. So now that is equals to, see, the value for K you can write it as a 2.303 into log. I'll write that is the value of K, 2.303 into log 4, that is equals to 2.303 by T into log of 0.9 divided by, if we'll subtract the 0.9, if we'll subtract the 0.675 from 0.9, we'll get an answer that is 0.225 till comes. Therefore, we can write it as a 900 divided by 225. Therefore, 2.303 log 4 is equals to 2.303 divided by T. If we divide this, we'll get that is 4. Then it will becomes log 4 till comes. Now, both the side you can cancel 2.303 and log 4. Therefore, T comes to here. Therefore, T is equals to 1 hour. It will take same time to convert, that is 0.9 mole to 0.675 mole of that is B.